Okay. Today we are very happy to have Xiaojian to give us his seminar. He obtained his bachelor degree from University of Science and Technology of China and his PhD degree in Texas A&M University in 2019. And then he became a postdoc research associate at Bielefeld University in Germany and currently is in Galilican Institute of High Energy Physics in Spain. And he's working on the thermalization of various forms of the QCD matter, including both theoretical and phenomenological aspects. Yeah, Xiaojian, please.
Thanks. Thanks, Wenbing, for inviting me to present this kind of research topic. So I'm going to talk about non-equilibrium QCD matter and the thermalization of this kind of matter. So here's the outline. I will first give a very brief introduction about the QCD matter from the picture of big band to the little band. Then I'm going to talk about the far from equilibrium QCD matter, basically the turbulent nature of the Quark-gluon plasma and the application of theoretical study of this kind of thermalization picture to the early stage of heavy-ion collision. I will talk about the pre-hydrodynamic QGP in heavy-ion collision and how we can probe this pre-hydrodynamic QGP in heavy-ion collision with different probes. And I will also talk about quantum speed up for the QCD matter, which is an exciting avenue for computing. So physics in physics is a natural science of matter, and we usually have two sort of philosophy. One of the philosophy is reductionist. So we can always find finer and finer structures and constitutes of those matters with higher and higher energy. Another sort of philosophy is emergence. So if we look at one water molecule, it's very simple. But if we look at snowflake, there are various forms of a snowflake. So this is the sort of phenomenon of emergence, and Anderson say this is much different. So the reductionism about QCD matter is the discovery of QCD theory itself. So this is one of the theories of finite structure experimentally verified. So back to the years of 1960, that Hagedorn found the number of hadrons they diverge when approach a certain temperature, which is the Hagedorn temperature, and that may indicate there's the absolute hot temperature, or it may also indicate there's new degrees of freedom beyond this temperature. So when we go to temperature beyond this limit, all hadrons are expected to be made of these new degrees of freedom. Then to the years of 1970, Gross, Wilczek, and Polyder defined a symptotic freedom, which won 2004 Nobel Prize. And the theory is called quantum chromodynamics. So the basic statement about this symptotic freedom is that the running coupling becomes weaker at a larger exchange momentum. This indicates that if we have higher and higher energy and larger exchange momentum, there might be a deconfinement and there will be free quark and gluons. And this is the new degrees of freedom we were talking about. And the emergence is, so when we talk about matter, we usually talk about matter constitutes of many particles. So in this sense, the free quark and gluons, they can form a new kind of matter, new phase of matter, which is called Quark-gluon plasma. This is believed to be the hottest matter in the universe, and it can only exist in nature a few microseconds after the Big Bang, because only in that time in the universe there's enough density and temperature. So we have a lot of technology to sort of observe or detect those matters, form of matters in the universe, and from telescope to satellite. And if we want to look at finer and finer structure, we need higher and higher energy. And if we want to look at the earliest time of the universe, we also need higher energy to sort of recreate this kind of matter. So in order to produce such a high energy, high temperature, hot dense Quark-gluon plasma, So people propose there's a heavy ion collision as a little band to sort of recreate this kind of matter. So basically, we smash the nucleus to produce bunker mediums of free quark and gluons. And Professor T. Lee said the nucleus as heavy, as weighty as balls, and the collision makes new rims. So this is more different, more different in high energy nuclear physics. So heavy ion collision is the largest experiment in human history back to years of 1980. To today, we have several experiment facilities to sort of study this form of matter, like the SPS at the CERN, RIC at Brookhaven, and nowadays LHC at CERN. The earliest signal of the Quark-gluon plasma is probably in years of 2000 that we people find gypside abnormal suppression at SPS energy at CERN. So if we calculate the suppression with just hydronic interaction, those curves shown in this plot, they cannot describe the experimental values. And it's worth mentioning that the theoretical prediction by Matsu and Sachs 15 years ago, before this discovery, is sort of already tell us gypside is a signal, sort of probe to discover the Quark-gluon plasma. And there are fruitful physics in heavy ion collision because it is a complex multi-stage experiment, which includes the initial production of quark and gluon, and also thermalization of this non-equilibrium quark-gluon plasma, and also dynamical production of hard and electromagnetic probes in QCD. There's also hydrodynamization because the expansion of the fireball cool down this temperature of the fireballs will eventually sort of confine again the quark and gluon degrees of freedom. So my talk will be focusing on thermalization of non-equilibrium QGP and the dynamic production of hard and electromagnetic probes in QGP. So first section is the far from equilibrium QCD matter, and we will talk about the turbulent nature of the QGP. So in order to study this non-equilibrium matter, we sort of implement a QCD effective kinetic theory, which can study this non-equilibrium QCD plasma, and this is a state-of-the-art tool to study this matter. It is the effective two-point correlation from the QCD, so we can rewrite these two-point correlations as a set of coupled Boltzmann equations for quark and gluon degrees of freedom. And in right-hand side, we have various collision kernels, basically including both elastic and inelastic scattering QCD. So you see there are many diagrams, but I will not go into details about this. When we talk about far from equilibrium system, we must talk about what kind of system we want to thermalize. So there are two typical far from equilibrium systems we are most interested in. The one is the occupied, over-occupied plasma. The other one is under-occupied plasma. So in the over-occupied plasma, in the initial separation of scale is that the initial momenta is much smaller than the equilibrium temperature, and there's direct energy flow, energy cascade from low energy to high energy. So you can see there's the initial distribution of gluon, and this is thermal distribution. There's energy flow from low energy to high energy. And this is interesting because it's essentially the initial state in the heavy ion collision, which is over-occupied gluons. The other typical far from equilibrium system is under-occupied plasma. So opposite to the over-occupied plasma, the separation of scale is that the initial average momenta is much larger than the thermal temperature. So we start with sort of mini jet at very high temperature, the small numbers, and there will be inverse energy cascade, sort of transfer energy from high energy, high momentum to low momentum. So this is also very interesting because this is essentially a picture of thermalization for the jets in the heavy collision. Okay. Now let's talk about how these two kind of systems are thermalized with a simulation of QCD effective kinetic theory. So the first thing we want to see is the over-occupied plasma. There's some turbulent signature of this plasma. So we know that turbulence is actually very complicated, but there is some sort of signature to see this is a sort of indicate there's turbulence in this kind of matter. So one of the application is self-similar energy cascade. So what it means is that if we plot the sort of the distribution function for gluon, we can sort of rewrite this with a self-similar scaling spectrum. And there's a universal scaling function with sort of scaling exponents. There's sort of kind of universal scaling exponents. So in this figure, I show the high evolution of the gluon distribution. So this is the initial distribution. You gradually change it until it's thermalized. And if we plot the universal scaling function here, we see at some certain time, all these universal functions from numerical simulation are collapsed into sort of a very narrow range. So this is the indication there's self-similarity in this evolution.
Sorry, how do you get scaling exponents alpha beta?
So you have to first do some small angle approximation to write this equation into Quark-gluon equation. You assume there's the sort of scaling, like what people usually do for classical turbulence. You assume this, and then you plug in this into equation, then you can extract those exponents. And it's worth mentioning that those scaling exponents are from Yamira's plasma, which is gluon only. And our simulation shows that the scaling works also for QCD plasma because the whole plasma is basically gluon dominated. And the Quark spectrum basically following this gluon spectrum.
Okay.
Another turbulence we can look at is sort of for the underoccupied plasma. We can find some Kolmogorov-Zakharov spectrum, which is sort of stationary solution, evolution. So Andrei Kolmogorov, who is working on classical turbulence, and told us there's sort of power law in classical turbulence, which is a very famous power law. And in our simulation, we also find very similar things. So we start with a sort of mini jet at a high momentum. And during this evolution at some certain time, for instance, here, we see there's some slope, which is indicating a power law in QCD turbulence. And this whole picture is called bottom-up thermalization. So we see these two types of turbulence signature here. Now we want to apply this QCD effective kinetic theory to study the early stage of heavy collision. So here is the sort of picture for different stages, for different stages of heavy collision. So the question is, where does this QCD thermalization occurs in the heavy collision, which is also called early stage. So we start with the initial collision to attracting nucleus. Then they traverse, and there is the sort of gluon flux, and they will sort of partnerize to become gluon particle. And those kind of non-equilibrium gluon dominate the initial particle at the pre-equilibrium stage can be described by this kinetic theory, and it will thermalize into sort of near equilibrium hydrodynamic state. And hydrodynamic state will last the longest time for in heavy collision until the temperature reach QCD phase transition temperature, and then you have sort of combine again to have hydronic states. And usually you use Monte Carlo method to simulate hadrons. And there's also finally some free streaming of those particles to detectors so they can detect it. So there are several properties of this equilibration or thermalization of the QGP in this equilibrium QGP stage. So initially we have gluon dominated and highly anisotropic matter. So gluon dominated because the initial production of the matter is gluon flux. So initial particles are gluon dominated. And there's anisotropy because we have spin directions. So of course the longitudinal direction and transverse directions are very different. So what happens is during the evolution time, there is isotropization and chemical equilibration. So this is easy to understand. So the thermalization first. So once you have thermalized state, it's basically isotropic, and you will have both gluon and quark degrees of freedom. So isotropization and chemical equilibration or quark production are basically the two main properties of the pre-equilibrium QGP stage. Now the isotropization is one part of the kinetic equilibration. So kinetic equilibration means you're going from a non-equilibrium distribution to an equilibrium distribution. So something worth mentioning is that there's a sort of universal attractor solution in hydrogen collision, which is a result of second law of thermodynamics. So we know there's anisotropization and isotropization. Why there's anisotropization? Because initially there's also non-zero expansion in the early stage of hydrogen collision that will sort of make the medium more anisotropic. But eventually there's interaction between those particles, and there's hydrodynamization or isotropization, of course, to sort of thermalize this particle. Yeah. So in this figure, I show the arterial pressure over energy density ratio of the pre-equilibrium QGP. So this is the indicator of the anisotropy of the matter. So we start with various different initial states. So initially, all those curves will drop down because of the anisotropization of the expansion. And eventually, and then at some point they will reach some point, and they will universally approach hydrodynamic limit. Eventually, they will thermalize isotropics. So basic feature, there are two basic features. One is memory loss. So different initial states will tend to reach a unique point at some point, even before the hydrodynamics become valid. And there is also universality. Once all those points reach this point, there will be universal sort of approaching to hydrodynamic limit. So this is called the universal attractor solution in Hamming equation. And another property, as we see, the chemical equilibration. So basically, we have to produce quark antiquark pairs from gluon. So here, I still show pressure over energy density ratio with different biochemical potential. So this basically indicates different amounts of initial quark numbers in the system. And in this figure, maybe more illustrative, is that so I plot this. This is the energy fraction of some specific species of particle like gluon or quark over the total energy density. And this is sort of the universal time. And usually, when this universal time equal to 1, this is basically the time when hydrodynamic kicks in. And from this figure, we can see that chemical equilibration actually finishes much later than hydrodynamization time, although at the same magnitudes. So the basic conclusion we can make from this is that clock will slow down this equilibration within this chemical equilibration process. And chemical equilibration persists after hydrodynamization. The reason for this is that there's different degrees of freedom for degeneracy factor for quark and gluon, and there's also different quantum statistical factors for gluon and quark. This is why quarks slow down this equilibration. So we've talked about attractor solution. So now we can talk about the application of this sort of attractor solution to some realistic problem. So we know thermalization is about change. So we sort of changing from non-equilibrium system to equilibrium system, which is very complicated. But there's certain things which is unchanged during thermalization, basically conservation laws in physics. So two of the main conservations in equilibrium stage is the energy and charge conservation. So with some argument of energy and charge conservation, one can derive sort of universal attractor solution, which can connect the energy density or number density at some specific time during this pre-equilibrium stage to the energy density and the number density to the initial state. So those are very simple formula just based on the conservation law. And this is sort of energy attractor plot, which is tau to the 4/3 times energy density over equilibrium ratio. So we can see we have sort of the different initial conditions of free spinning state and emerge to sort of a unique point to hydrodynamic limit. This is sort of more universal than the isotropic pressure attractor plot. And one of the applications for this kind of simple conservation law attractor solution is that once we know this, we can sort of know the trajectory of the Quark-gluon plasma QCD phase diagram. So this is a typical QCD phase diagram with a function of temperature and biochemical potential. Although I just plot part of it, and this is hydronic state. This is basically the Quark-gluon plasma state. And we start with upper right corner, and evolution or thermalization of this matter will drive these points from this upper right corner to lower left directions. And those dashed lines indicate the pre-equilibrium stage. Those solid lines are indicating the sort of hydrodynamic state. So this is one thing. And another thing we are interested in is that, so we sort of talk about attractor, which is sort of universal behavior during this thermalization, and we can use this attractor solution to simplify some of the calculation, provide us some insights on QGP evolution and QCD phase diagram. So this is about the bulk median in average, the attractor solution. But we know that during this sort of equilibration, there's also hotspots as a fluctuation. So at different location or position of the QGP median, there's sort of fluctuation makes some of the place hotter, some of the place slightly sort of cooler. So in order to catch this kind of physics, we can sort of still use this kinetic theory to catch this physics. But because to evolve kinetic theory with the full phase space of position and momentum is very expensive, so we use linear response theory to linearize this kinetic theory. And we can calculate energy momentum tensor and track current vector response to perturbation to fluctuations and hotspots. So once we calculate those response functions and with a convolution of this light cone of the space from the initial state to the hydrodynamic state, we can know the energy momentum tensor and track current vector as function of position with different fluctuations at hydrodynamic state. So in this figure, I should illustrate this kind of picture. So you start with sort of fluctuated initial state during this thermalization process. It will sort of smear out some of the fluctuation properties in this matter. And by doing this way, we can sort of provide a complete picture of the pre-hydrodynamic plasma in high ventilation initial condition for the hydrodynamic simulation. Because for most of the hydrodynamic simulations on the market, people just use the initial condition here, which is not complete initial condition for the hydrodynamic simulation. Of course, when we talk about the early stage of the high ventilation, we must also think about how we can measure this early stage, because time is very short. So again, we look at this figure, we see this kind of pre-equilibrium stage. The time for this pre-equilibrium stage is much shorter than the time for the hydrodynamic stage. And again, there's the two main features, isotropization and chemical equilibration. Yeah. So one of the possible probe to sort of help us understand or measure this pre-equilibrium stage is the electromagnetic probe, such as di-lepton photon, because there's no further interaction with QGP. So those interactions for di-lepton photon with a media must be through QED channel, which is much smaller compared to QCD interactions. This is why this is a very neat probes to probe this stage. Okay, so di-lepton calculation in heavy collision, we're focusing on thermal productions on the market, and we claim that they can provide a sort of speedometer to measure the isotropization or chemical equilibration of quark and anti-quark production. So again, we start with the initial state, which is the gluon-dominated anisotropic matter. And the next step is we have to first produce quark and anti-quark pairs from gluon. And then we can have a second step to produce di-lepton pairs from the QQ bar annihilation to virtual photon channel. This sort of catch the chemical equilibration. And of course, when we calculate di-lepton production sort of yields, we have to use the quark anti-quark distribution as an input. So it not only catch the chemical equilibration, it also catch the isotropization of the plasma, because initially anisotropic medium will also produce anisotropic quark and anti-quark pair distribution. So in this figure, I show the two figures, very simple to show these effects. You don't have to ask the details about these figures. What happens is that in this figure, this is basically the yield of di-lepton over ideal ratio, which means ideal ratio means it's thermal, assuming the median is thermal equilibrium. So if the median is in thermal equilibrium, of course this ratio would be equal to 1. But we take into account the chemical equilibration of during this pre-equilibrium stage. So there's deviation from 1. And of course, we have to wait for these quark anti-quark pairs to produce the di-lepton pairs. So the total yield will be suppressed. And in this figure, so if there's if we assume the state is isotropic, this quantity should go to 0. But we see there's connectedly anisotropic median, so this deviates from 0. So those are sort of di-lepton production to see this, to effects from theoretical calculation. And of course, in order to provide di-lepton as a nicer probe to probe frequency, one have to calculate di-lepton production for all stages, from QGP and hydronic stage, sort of put all of them together and check the place where pre-equilibrium stage contributes, see how much and whether we can sort of see these effects in experiments. So another probe is hard probe. Okay. So why is hard probe interesting? Because it has distinguished scale compared to the thermal QCD plasma or non-thermal QCD plasma. So hard probe usually has a very large energy, like a jet or heavy quark. So jet is a particle with very high energy, not necessarily very large mass. And heavy quark usually it must have a very large mass. And it can be a low velocity or large velocity. If it has a very large velocity, it's a heavy quark jet. Okay, and the temperature of the median is basically connected to the energy of the light pattern or those light quarks and gluons in this QGP. And we claim there's also different time scales during this thermalization. So first, the heavy quarks, it has very large mass, or jet, it has very large energy. So the initial production of those hard probes occurring at very early time. And the QGP thermalization is basically inverse temperature dependence. Of course, there's some other coefficients I just neglected. And the heavy quark thermalization is can be rescaled with mass over temperature ratio. QGP thermalization temperature that time. So now we see that we have several time scales in thermalization. First, you have to produce hard probes, and then there's the thermalization of QGP. Then there's thermalization of these hard probes. So a typical picture of simulating hard probes in sort of QGP phase is with Brownian motion. So this is heavy quark, and you have sort of kicks, stochastic kicks from this medium. So again, we look at the picture of heavy collision. Those are different time scales according having different stages of heavy collision. So heavy quark simulations for the heavy quark energy loss and momentum broadening on the market currently are basically focusing on the hydrodynamic stage. So one of the reasons that hydrodynamic stage lasts for a very long time, and it's in a thermal, so basically near thermal medium. So the calculation is also simpler. Now the question is that whether the heavy quark energy loss in the early stage, for both plasma stage and the kinetic theory stage, whether they are important. So we know there's the expansion of this fireball, so the temperature of this matter will drop down. So we know the density will drop down. So we argue that at early time there might be very dense medium. So that means the heavy quark energy loss or momentum broadening or any transport property can be very significant as well, although the time for this early stage is very short. So how do we model the heavy quark dynamics? So heavy quark usually has a large mass, and that means usually it has low velocity, which means the dynamic heavy quark evolution is from elastic kicks from the medium. It will dominate. Of course, there's also radiation, but that will be suppressed compared to this elastic kicks. So one of the model is this kind of stochastic differential equation for the heavy quark dynamics. So this is stochastic differential equation called Langevin equation. So you have two contributions. One is the drag term, the other one is diffusion. So drag means whenever your momenta is for the heavy quark, it will always drag this momenta to zero. We have this kind of force, drag force. And the diffusion means whenever the momenta is, it will have some momenta broadening, so to sort of smear out the momenta distribution of the particle in momenta space. So you combine these two effects, okay? So eventually, the heavy quark momenta will be close to zero, but it will also have some smearing sort of diffusion. So these two effects will compensate with each other, so compete with each other, and eventually there will be thermalization for the heavy quark. This is also sort of the result of fluctuation dissipation theory. And okay, and also you can use Ito's lemma to transfer this stochastic differential equation to a partial differential equation, which is called Quark-gluon equation. And you can calculate those transport coefficients from Rice approach from QCD physics. Okay, now let's look at this heavy quark in pre-equilibrium stage. How do we calculate the transport coefficients? So those are formula for calculating the Jack and diffusion coefficients. So basically, what's important is that there's some distribution for it's depending on the distribution of partons in the medium. Okay, and we see there's several effects for this distribution. So first, there's an anisotropic matter to isotropic matter. So in this figure, I show time evolution of gluon distribution momenta space in transverse and longitudinal momenta. And for quark, this is your quark. So what happens is that initially you have very anisotropic momenta distribution for gluon, and it will evolve, become more and more round. Eventually, it will be sort of isotropic. And chemically, initially there's almost no quark. There's also production of quark and quark pairs. So this is second effect, as we mentioned also in previous slides. And also remember there's expansion of this fireball, so there's sort of transition from higher temperature to lower temperature of density during this evolution. Now let's look at the transport coefficients we calculated with pre-equilibrium QGP, which is simulated from QCD effective mechanics theory. This is the time evolution of this pre-equilibrium transport coefficients for the Jack and diffusion coefficients. We speak the coupling, and this is universal time. So we see the drop down of these sort of coefficients for both Jack and diffusion. So this is the effect of density drop. And then this dashed lines for the contribution from the quarks. Quarks is the partons in QGP. And we see there's increase of quark abundance, quark contribution at an early stage. And at a later stage, there's also density drop. So the coefficient will also drop. And also, it's interesting to look at the isotropization also in this figure. So because we assume, for instance, we assume the direction of heavy quarks along x direction. Initially, there's an anisotropy between xy plane and z direction. So initially, sort of the transport coefficient, which is perpendicular to heavy quark, y direction and z direction, they are very different because there's anisotropy, which can be shown here. This is green line and blue line. Initially, they are very different, and eventually, at some early stage, once the median is basically thermalized, all this green line and the blue line they merge together. This is an indication of isotropization. And one can also directly look at angular dependence of regulated transport coefficients to sort of see this isotropic effect. So by doing this, we release our constraint for the heavy quark direction to point to x direction. We make the heavy quark in the xz plane. So what is happening is that, so once we have isotropic median, we are not pointing to different directions here. We only have diagonal terms for the diffusion coefficient tensor. Now, if we point this to z direction, so xz plane, you can sort of know the isotropic effect, and there's also non-trivial off diagonal terms diffusion tensor. So my next topic is about the quantum speed out for the QCD metric. So also still about heavy quark simulation. So when we talk about quantum computing, there's a lot of there are several types of quantum computing. So what I'm going to talk about is a gate-based digital quantum computing. So quantum computing is the parallel computing in nature, so it can potentially speed up calculation. And this kind of gate-based digital quantum computing is very similar to a classical digital computer. So this is the typical sort of classical circuit for a classical computer. So the classical bits 0 and 1, and there's typical classical gates, AND gate, NOT gate, OR gate, typical classical circuits like adder multiplication. And for the quantum circuit, this is a sort of quantum circuit for this digital quantum computer. You see, there's those are different gates. And what is different from quantum from classical to quantum is that instead of 0 and 1 state, one can also have superposition of them and with a quantum phase. Sort of present here. And the typical quantum gates are X gate, which is basically NOT gate, Y gate, which is rotation gates for the phase, and Z gate, which is a phase flip. And there's also a Hadamard gate, sort of providing the superposition of different states. And there's various typical quantum circuits like adder and a Fourier transform. So what happens, we want to simulate heavy quark stabilization on this quantum computer. So we have multiplication for this operator for this term, and we also need to have quantum random number generator, and we also have some quantum adder algorithm to add this up. So we first design this kind of circuit. This UL is the initial loading of the initial state. UW provides this random number generator, so the stochastic force to simulate this stochastic force and the diffusion of the heavy quark. Then UA is sort of the adder circuit to add them up, so you have both drag and diffusion components. And you have some reset gates to sort of clean up those memory of those registers. So this is one of the circuits we sort of firstly construct, which is called quantum circuit Monte Carlo method, to simulate heavy quarks simulation. And another method is the accelerated quantum circuit Monte Carlo, which is the result of quantum speed up. So what happens is that instead of this reset gates, we use the tower structure of this quantum circuit. The reason is that when applied to kind of quantum amplitude estimation, it requires a graph operator that can be constructed with unitary circuits. So without reset gate, we can construct a unitary circuit to perform this QAE. And this QAE is the core of the quantum speedup. So once we have sort of state, so this state assigned to represent the momentum space of this heavy quark, and we have and select qubits, we can prepare sort of oracle, which is also operator, to make a superposition of new bases, and the expectation value can be calculated from this sort of. So this is a momentum distribution which can be represented like this. And any expectation value, for instance, if you want to calculate energy, average energy or average momentum or momentum squared to see how much is the momentum broadening and how much the energy loss, you have to use this kind of formula to calculate. They can calculate from this sort of formula, and we iterate this Grover's operator. We will have a superposition of two states. One is called bad state, the other one is called good state. And the good state is some state we're anxious for. And after we calculate this, we can, of course, calculate the probability of bad state and good state. In this sense, we can calculate this. So, for example, we assume there's the the n number of sampling. So we assume there's H results in a good state and n minus H results in a bad state for the measurement. Okay, we can calculate sort of likelihood function for this kind of event. And we can also calculate combined likelihood with different depths or different numbers of iterations. And in those are very technical things, but in the next slide, I will illustrate you why this is useful. Okay. So initially, if you calculate likelihood function with just one iteration, you will have this kind of distribution, and this peak value is sort of the value you want to measure. And with various iterations, this kind of distribution will sort of split out into different peaks, and then there will be higher and higher precision to sort of locate these peaks. But also you have to do this combined likelihood function, so to sort of multiply all these distribution functions together. So eventually you can rule out the irrelevant distributions here, and the result is that you can more precisely locate the distribution you want to measure or the value, and let's say the energy or the momentum square you want to measure for heavy quark with this method. So the quantum speedup is that from information theory, from official information, people find there's a lower bound of errors with this method. So from quantum perspective, there's the error lower bound is 1 over n dependence. This n is number of core. You can think of this core as the number of total operators you have to apply to the circuit. And with the classical method, the information theory says the dependence is 1 over square root of n dependence. So in this sense, we see the quantum method has some quadratic speedup compared to classical method. So this is some benchmark of classical method error and quantum error from this literature. You can see from different sort of values or expected values they want to measure, the quantum strategy has advantage at larger number of. And here are simulation results on heavy quark simulation. So we compare the direct measurement and the QAE measurement. So you can match with each other. And there's a pattern of simulation of sort of histogram of distribution for heavy quark with test particle compared with theoretical expectation. So we see there's a small deviation from these histograms to the theoretical expectation. This is due to the lattice effect because we're not choosing enough small enough time step. Once we have sort of small enough time step, we can have have a very nice matching to the analytical results, although it's very expensive with the current hardware you can calculate. Another thing you can calculate is sort of V2 if you have assumed you have an anisotropic medium, like in the initial stage of the heavy collision. So you can see at different time you gradually build up V2 for the heavy quark. To better illustrate this kind of effects during for the heavy quark simulation with this quantum simulation, we show this time evolution of density in winter space. We see in the upper panels we see the we start with sort of very nice initial state, and along the time thermalized to a very long density, momentum density, and with an anisotropic medium we can find the evolution will tend to be have some elliptic sort of shape of this momentum density distribution. So now here's the conclusion. So we talk about the philosophy, start with the philosophy of reduction in convergence. And we talk about the far-from equilibrium QCD matter, the tool we implement, and the physics we study, basically self-similarity and chromodynamic spectrum as a signature of turbulence. And then we also apply this tool to study early stage heavy collisions, like the kinetic and the chemical equilibrations and attractors. We talk about fluctuations, how we can provide a complete picture of the turbulence state of the heavy collision, and to sort of provide a very realistic initial condition for heavy, so for hydrodynamic simulation. And we also propose that di-lepton can be a probe for hydrodynamic QGP in heavy collision. We also discuss a heavy quark dynamics and heavy QGP in heavy collision, which can be further implemented into heavy quark simulations currently in the market. Then we talk about the quantum speedup for the QCD matter, basically the heavy quark simulation on the quantum computer, and how this quantum speedup can happen in this method. And thank you for your attention.
Okay, thanks again for this comprehensive talk. Do you have questions?
Yeah, I have one question.
Yeah.
Oh, just a question. So here the quantum computer is actually a real quantum computer, or it's kind of simulated on some traditional computers?
Okay, it's a simulator in a classical computer.
Oh, okay. So, is that kind of practical to actually do that on some certain real quantum computer in the future, or it's still practically not accessible?
Okay, so the current status of free, open, collectible quantum computer you can access is probably the IBM quantum computer. With the free version, the maximum free version is 7 qubits, which is very small compared to the qubits we need. So for the moment, but maybe in the future, some other company or IBM can release some sort of larger size of quantum computer to do this kind of simulation. Yeah.
Okay, so how many bits do we need here?
So for instance, here for each register here we have 4 qubits. So 4 qubits means we have 16 states, and this just for one register. And we have multiple registers. For example, if we have other iterations, and for each iteration we have basically 2 registers for the random sort of random number generator, and for this momentum space. So you need 8 times n sort of qubits.
Okay, thank you.
Can I ask a question? I'm not sure whether the kinetic theory that you based your results on, and also hydro, are these classical theory, or there's some quantum corrections to it?
Okay, so obviously this so the hydrodynamic theory and the kinetic theory are basically semi-classical. So the reason is that the equation, the ruling equation, for instance, the Boltzmann equation for kinetic theory and the hydrodynamic theory, which is the evolution of the tensor, are classical equations. But you have to calculate those transport coefficients, which is from quantum field theory. And for the for the kinetic theory, it's a little bit more quantum than the hydrodynamic theory because the collision kernel, not only some transfer coefficients, but those collision kernels have to be directly calculated from quantum field theory. So it's semi-classical.
Semi-classical. So you do incorporate some of the Feynman diagrams into it in a perturbative sense, right?
Yes. So currently so sort of this. So we are calculating these diagrams at the leading order, and you calculate them, and you can calculate this collision integral. So basically the transition, the metric amplitude square times some statistical factor, which also catch some quantum statistical effects into this collision integral. This is what we calculate.
I have a question. So I'm just wondering, how important is the energy loss of heavy quark at the pre-equilibrium state?
So I have a very qualitative argument that at a pre-equilibrium state, although you have very short time, but you have very, higher density. So it can be important. But how much, how important it could be is that we have to sort of simulate the heavy quark sublimation or energy loss, both in two stages and compare it. And then we can draw quantitative conclusion.
So can you see that there's still energy loss of heavy quark in small systems such as PLAD or PH or even PP?
Yes. In PP, I'm not sure because the size is too small. But so in principle, there's always some energy loss because the heavy quark or jets, they always have to traverse this kind of matter, whether it's small size or large size, and whether it's cool enough or hot enough. But the question is how important it is compared to vacuum.
Okay, so yeah, I'll wait for your next result to quantitatively give us result. Okay. Do you have more questions? Okay, no more questions. Next section again.